Okay, let's start the second talk of the afternoon session, which is the last talk. So the speaker is Alison Warman from Oxford, and she'll talk about logical gates of arbitrary precision in 2D topological non-abelian codes.
Thank you very much to the organizers for putting together this very nice workshop, and to Ryohei for giving a very nice introduction to this talk. So I will talk about these arbitrary precision gates, so how we can get arbitrary logical levels of the Clifford hierarchy purely in 2D, but using non-abelian codes. This is work in collaboration with my supervisor, Sakura Schaefer and Namiki at Oxford, and with Shenji Huang and Yanzu Chen at Florida State University. So as we heard, the Bravi-Koenig theorem strictly bounds the constant depth logical gates that can be obtained in Pauli stabilizer codes. And in the context of Pauli stabilizer codes, lattice surgery is one way to implement Clifford or logical operations. However, what if we want to remain in a low number of spatial dimensions, but go beyond Clifford logical operators? So Margarita Davidova and Don Williamson and collaborators showed that using this twisted quantum double of Z2 cubed, one can get like magic states. And as we heard in Ryohei's talk, it can also be used to construct transversal logical gates. And another related work is instead using some like non-abelian lattice surgery to get instead CCX gates. So the motivation for our work is that certain quantum algorithms, for example, the quantum Fourier transform, rely on these small angle rotation gates. So it might be it's probably resource efficient and from a fault tolerance perspective to be able to implement them natively in a topological code. However, Bravi and Koenig proved that if one considers a topological code, so in like low spatial dimensions with local nearest neighbor checks and with only Pauli stabilizers, then the logical gates are strictly bounded in that if one wants a logical gate at level n of the Clifford hierarchy, then one needs to go to n space dimensions. So one can obtain only Clifford constant depth gates in 2 spatial dimensions, and these are not universal. So how can we go beyond the limitations? An answer is to use non-abelian codes. So if we use 2-dimensional topological codes rather than based on Z2, based on non-abelian groups, for example, these dihedral groups, which are the groups of symmetries of a regular 4-angon, then we can get arbitrary precision logical gates purely in 2D. So we can completely collapse the Bravi-Koenig spatial bound because we can obtain them still remaining strictly in 2 spatial dimensions and with local nearest neighbor checks. But as we will discuss, these will actually involve Clifford hierarchy stabilizers. And in particular, if we want level n in the Clifford hierarchy, the stabilizers will be a level n-1. I will discuss 2 approaches. One, which is a hybrid lattice surgery, where we will perform merge and split operations between different code patches. And the second one is this constant depth implementation, where we use automorphisms of the code to implement like a constant depth gate. Now, just to review the Clifford hierarchy, the Pauli group is defined as level 1. Then the Clifford operators conjugate Paulis into Paulis, as we know. And then recursively, one can define level k in the Clifford hierarchy to be the unitaries that conjugate the Paulis into level k-1. And our setting, so what will enable us to completely collapse Bravi-Koenig to 2 spatial dimensions is using group quantum doubles. So these are codes based on a non-abelian group, and these are topological codes. So they don't have good encoding properties, but they have, we expect them to have good fault tolerance properties because they're topological. The Hamiltonian has these nearest neighbor checks, vertex and plaquette operators. So the Hilbert space is spanned by group elements, And I will actually show that if the order of the group is a power of 2, we can actually map it to a purely qubit Hilbert space. And then the Hamiltonian has these terms. It's basically a generalization of the quantum double, the Kitaev Hamiltonian for Z2. And it was actually already present in Kitaev's 97 paper. Now, the vertex terms are like this. They generalize the XXXX check. But now we have left and right multiplication operators for the group elements. And then the BP terms generalize the ZZZ checks. And in this case, they basically take the product of group elements with their orientation, and we project it onto the identity. So in gauge theory language, like this imposes trivial charge, and this imposes trivial flux. And furthermore, we will consider codes on manifolds of boundaries. So one must also have these boundary terms. Okay. Now, we see that these operators that form the quantum double actually obey an interest in algebra, which is in particular non-commutative if the group is non-abelian. So for example, we see that the A operators multiply according to group multiplication. But for example, if GH is not equal to HG, then they won't commute. And furthermore, basically these B operators measure the flux around a plaquette. But if we act on them with an A operator, it will conjugate it. So we see that there's also some non-trivial action of AG on BH, which maps it to BGHG inverse. Note, however, that the term that actually appears in the Hamiltonian is the project onto the identity, and this remains invariant. Okay, so this is the quantum double algebra, and the anyons, which are topological lines in spacetime and which are the errors, if that can take us out of the code space, are actually labeled by a conjugacy class of the group and a representation of the centralizer. So in particular, they generally obey non-invertible fusion rules. The electric charges are the ones that are labeled just by representation, and the magnetic fluxes by a group element. And then we can also have the ions. Okay. And we will see that these codes can be defined, as I said, on manifolds of boundaries and with particular boundary conditions labeled by subgroups. Okay, let's start with hybrid lattice surgery. So in this case, we consider this a square patch with with boundary conditions that are the same on opposite boundaries. And we will take the top and bottom boundaries to have smooth boundary conditions, so where the subgroup K is equal to G. And this means that all group elements can end. That's why it's smooth. And instead, on the left and right, we'll have rough boundary conditions where only the identity group element can end. So in this setup on a square patch, we will have a basis of logical states that are spanned by group elements, and the logical operators which on the boundary can be written like this, with the left group multiplication operators. Now, if we have two code patches, like for DG and DG prime, we will first make sure that they are in the code space, so they minimize the Hamiltonian operators in their respective patches. And then we can merge them by first introducing ancillar qubits, group qubits in the identity state. But then, as we see that if we initialize them in the identity, they will automatically minimize the BP operators of the Hamiltonian, the ones that ensure trivial flux because they're on the identity. But in order for this full thing to then be in the code space of the merge code, we need to measure these AVK diag stabilizers. So basically the AV stabilizers across the interface. So we see that these are like entangling operators that are defined from a subgroup K diag of this G times G prime, where we have some elements H and then the projection. So where this P is basically group homomorphism between G and G prime. Okay, and by basically measuring these projectors across the boundary, we will entangle the two patches. And this performs a rough merge, because after this operation, the combined patch will be in a ground state. So it will give us a code. If we want to split it, conversely, we need to measure these qubits and then return them to the identity state if they're not the identity. So after this merge and split operation, we will have entangled the two patches. And we see that, remember that the logicals were these operators acting on the horizontal group qubits here. So we see that after this operation, we're left with basically the action of the right logical acting by H and the left one acting by this P of H. Okay? So how can we use this hybrid lattice surgery to create magic states or non-Clifford gates in the surface code? So our aim is to generate, in this case, a T gate in the Z2 surface code. Now we will start with the Z4 code, then merge and split into D4, which is the semi-direct product of Z4 and Z2, where here R labels the rotations of a square and S is the reflections, which then commute. And then we will do again merge and split into Z2. So we will start with a stabilizer state for Z4. So this is a stabilizer for Z4, but we see that crucially it has this phase, which is actually, will give us a magic state in Z2 or, non-Clifford T gate. So, however, this can be prepared in the Z4 code because it's a stabilizer state for Z4. Then to merge and split into D4, we basically want to teleport this state from Z4 into D4. And we do this simply by gauging Z4 diag. So this is just a diagonal where M is the Z4 generator and R is the generator of Z4 in D4. We merge and split them, and this simply teleports the state into the D4 patch. Now, to merge and split into Z2, we first perform this operation, which, as we see, entangles the patches, the D4 and the Z2. And then we basically apply these operators on the boundary of the Z4 patch. And finally, we measure out the identity logical state in D4. So this combined logical operation is actually equivalent to the T gate. Okay. We can also write the circuit for it. And in this case, the circuit also takes into account the possibility that when we basically measure these operators, we may not get the identity. And in that case, we can correct it by applying these rotations. So from the point of view of the error correction, as we reviewed, the quantum double algebra is actually non-abelian. So we will see later on in more detail that the stabilizers don't all commute. And in particular, we will have some terms appearing on the right-hand side. So we'll have commutators of stabilizers that are not zero, but give some other stabilizers. So the key for the error correction will be to first basically correct the errors that are violations of these stabilizers, which correspond to non-abelian anyons. And this will project us to a code where now the remaining stabilizers do commute, which means that the errors are now just abelian anyons and can be corrected in by standard means. That protocol of merge and split from Z4 to D4 and then Z2 can actually be generalized to D4N codes, where we have, rather than a Z4 subgroup, a Z4N subgroup. And again, we can input a stabilizer state for Z4N and then teleport it into D4N by gauging this diagonal subgroup. And then do exactly the same operations between the D4N and the Z2 patch to entangle them and then change boundary conditions to then obtain a T to the 1 over N gate. Okay. Also, we can consider other groups like S3, in which case we have Q-trits and qubits. And this can be used basically to input a stabilizer state, for example, for the Q-trit, and then again, teleport it into the non-abelian code by gauging the diagonal, and then merge it into Z2 and change in boundary conditions. And this is a way to basically take a stabilizer state for Z3 and give us a magic state for Z2. And this is actually beyond the hierarchy, the Clifford hierarchy, because it actually has this e to the 2 pi over 3 phase, although we need a Q-trits for this. And conversely, we can also input a Z2 stabilizer state, and then again, like teleport it into the S3 code, and then merge and split with Z3 to obtain a Z3 magic state. Okay, so to summarize this part of the talk, we've seen that we can extend lattice surgery from the surface code to these non-abelian codes where we have two possibly non-abelian groups, G and G prime. We initialize the codes in their ground states, and then we add ancilla qubits in the identity states. These automatically satisfy the BP terms of the full code, but they don't satisfy the AV terms, so we need to measure them. We need to apply these AV projectors along the interface, and this will then give us a merged patch this creates entanglement between the two codes. We can then measure them out, and basically this can be used to teleport some states from one code to another. So in particular, starting with some stabilizer states for like a higher abelian code like Z4 or Z4n, and then teleporting them via the non-abelian code into Z2 code to create magic states and non-Clifford gates. Now, importantly, since all these operations are topological, these operations are basically like topologically protected, and they only require nearest neighbor interactions here across just along this interface. Okay, are there any questions on this?
So in practice, I guess we have to realize qubits by collection of qubits, and some natural qubit operation you assume here will be expressed in terms of kind of noisy interqubit.
Yeah, we'll talk in more detail about the mapping to qubits in the second part of the talk. But yes, basically, if the order of the group is a power of 2, you can then map it to qubits. But importantly, the structure is still the non-abelian group structure. So it's still a topological code for the group.
Yeah.
Which is why, it's basically this non-abelian group structure, which still maintains basically the topological properties of the code. Yeah, we'll discuss the decoder, like the error correction, in like the third part of the talk. So first I'm discussing the ways to get the logical gates, and then we'll discuss the error correction. Okay, now let's see a different approach, which rather than using letter surgery, creates these constant depth logical gates. And this generalizes the work that we heard about in the previous talk by Ryohei, Guan Yu, and Prashen. Okay, so here we will take logical states to be encoded in the non-abelian code via these trivalent configurations of anyons. Okay, so since these are basically non-contractible, they will give us inequivalent ground states of the Hamiltonian, so inequivalent logical states. And we will choose them to encode a logical qubit. So once we have our logical qubit states, we can then perform an automorphism of this code that preserves the boundary conditions, and that will realize a logical unitary. So the automorphisms we will focus on are defined basically by SPT stacking. So mathematically, they're characterized by a group 2 co-cycle. So this is like it has a representative like alpha G1, G2 that obeys a closure condition. And since this is a manifold of boundaries, we also need to require this alpha to be trivialized on the boundaries. So there will also be these boundary functions or one code chains beta. Okay, so the logical action will just be given by this group 2 co-cycle alpha, and then with the boundary counter terms, B1, B2, and beta 3. Okay, one for each boundary. Okay, so this is the logical action. And we'll see that for these codes based on the quantum double of D4n, we can get constant depth unitaries at arbitrary level of the Clifford hierarchy, okay, just by increasing this D4n. While remaining purely in 2D space, and here we're evolving in time, showing how our protocol is being carried out.
So when you say constant depth theory, you're assuming you have qubits where the value of B is changing. Is that right? You're not going to get, this is not claiming it's constant depth for qubits, is it?
It's also constant depth for qubits. Okay. Once you fix a code, D4n, it will be constant depth also for the qubits. Like once you fixed it. But yes, no, okay, I understand your point that indeed, like it's not constant, like the depth increases. No, I mean, yeah, the depth increases with n, yes. But once you fixed an n, it's constant depth. Yeah, I agree. But if you want to increase n, you need to increase that in the qubit basis. Okay, so as we've seen, the Hamiltonian has these AV operators and the BP operators. And actually, these terms appearing in the Hamiltonian, these are basically the sums of, these are now projectors, commuting projectors. So the ground states, i.e. the logical states, actually have to minimize the bulk AV and BP terms and the boundary ones. So in particular, we can write the trivial one by just taking the tensor product of identity group elements and then apply it, which automatically minimizes the BP terms, and then applying the product of AV terms. Instead, to get a non-trivial logical state, we need to take a non-trivial configuration of these anyons labeled by group elements, where here we're basically applying these like ribbon operators for these group elements on the trivial state. And then again, we have to apply the AV operator. We need to choose like G1 and G2 to fuse to G1, G2 in order for this to be in the code space. Okay? And we will choose them to encode a logical qubit. Now, if we have a logical qubit, then we also want some logical operators. Now, as we heard also in Ryohei's talk, we can have this logical Z, which is defined very simply in terms of these one-dimensional irreps, row 1, row 2, and row 1, row 2, where these are just one-dimensional. So this operator is a very standard like product of Pauli Z's. Okay. Now, what's more subtle is the logical X. So basically, the anyons aren't actually labeled by group elements, they're labeled by conjugacy classes, which contain typically more than one group element. So the logical X written in terms of anyons is actually not invertible. However, if we choose particular boundary conditions, for example, if we choose a boundary condition labeled by these subgroups K1 and K2 such that the intersection is only a single group element, then the boundary conditions actually pick out one group element here, and then the fusion constrains this third group element to be the product. So there is actually a way to define a logical X that is invertible like this. However, in order for it to like square to 1 without generating an error, we need to be careful in how we take its product, and we need to basically perform this kind of sweeping action where we see here that the blue G2 group element will act by conjugation on G1, G2, okay, as follows. And then if we require these conditions on the group elements, this will actually square to 1, but only if we compute the fusion like in this way, which is not the naive kind of product of operators because it has to take into account this conjugation action. Anyway, from the braiding of the anyons that we require to have a minus sign, we get that these logical operators anti-commute. So we can basically define the Z eigenstates as the logical 0 and the logical 1. So once we have our logical states, how do we implement a constant depth logical gate? So we will take a configuration of these like group elements, which can be identity or can be non-trivial. And then we construct this logical unitary U from a group 2 co-cycle, which obeys this closure condition, and boundary 1 co-chains that trivialize it on the boundary. As I said, because this is a manifold of boundary, it has to trivialize in order for this to end. So the full U will act trivially on the 0 logical state and will act with this phase on the 1 logical state. And because it comes from an automorphism, it's a topological operator. Okay, so concretely on the lattice, we see that if we have this, typically we have a group element basis. So on the group element basis, these betas are boundary functions acting on a single group element. So they act as follow on an edge along the boundary. Instead, alpha is a group 2 co-cycle that acts in the bulk, and we can compute its action by triangulating the plaquette. Okay, so then we can write this circuit for the unitary, and indeed we see that it is constant depth in the group basis, but it will actually increase with n in the qubit basis. Okay, so for D4n, the group of symmetries of a 4n gone, we have the rotations and the reflections, and importantly, we have these one-dimensional irreps, 1R and 1S, which are +1 and -1 as follows. So we can use these irreps to define a logical Z. Okay. Now, the 0 state is just this trivial state, whereas the logical 1 will be defined with these like anyons coming from these 3 group elements, IS, S, and R. Okay. And because of these properties of the one-dimensional irreps, this will have like eigenvalue -1 under Z. So this is like a logical qubit. Then we can compute the non-trivial group 2 co-cycle. And in particular for our group elements of interest, it's like the 2 co-cycle is basically 1. But then when we trivialize it on this boundary, the one labeled by the R subgroup, okay, there's a boundary here labeled by the rotation subgroup. And notice that this subgroup is R to the 4n. So when we calculate this alpha equals delta beta, this basically gives us equations for beta, and we have to take these roots. So the solution to this is that beta is e to the I pi over 4n, okay? So when we plug it into this expression, we see that it's just 1 on the trivial logical state with just identity group elements, but then it will give us this phase on the RS state, which is the 1 logical state. So the logical action is that of t to the 1 over n. So we can also write the stabilizers of this code quite explicitly, where we have these AV operators, where which are comprised of left and right multiplication. Here, cal x is the for-dit, like this for-and-it multiplication operator. Instead, this z is the qubit operator, z, okay? Anyway, so we can write the AV operators, which are unitaries. Instead, the BP operators are generally projectors. So if we want a stabilizer group with unitary operators, we need to take linear combinations of these BPs to make unitaries here. And then we can compute the commutators, these group commutators. And as I mentioned before, we see that they don't close, but they give some other commutators. However, notice that there's some nested structure. So if we basically calculate like R and S, we get R to the -2, so we get these higher powers. So the idea for the error correction will be to basically correct them sequentially. First, we correct like the right-hand sides, which will be non-abelian anyons. And then we will be left with commuting stabilizers, which are abelian anyons. So as we already mentioned, we can map this to a Hilbert space spanned by n qubits when the order of the group is a power of 2. And now I also want to mention that this is not a sufficient condition. Like this doesn't happen necessarily for any group. I mean, it also must have some nice properties, which in the case of D4n, the dihedral groups is like super solvability. So we can write it as a sequence of central extensions of Z2. And this enables us to map it to a qubit Hilbert space. So the map is actually quite simple because we have like n-1 qubits for this like Z4n factor, where we basically have all these like powers of n, so r and then r squared and then r to the 4th, etc. And then we have another qubit for the reflection s, okay? So concretely, if we have our group element like this, we just take the binary representation of A and then J, which is already a qubit, okay? So this maps it to a qubit Hilbert space. But we see that the operators that appeared in the stabilizers, and these were the operators for the for-and-it, like cal x and cal z, they now get in the qubit basis, they have higher Clifford levels, okay? However, we see that the level of the stabilizers is always one less than the level of the logical T-gate, okay? So this actually suggests a generalized Baravi-Koenig bound, which I will comment on at the end, okay? Now let's see a more detailed error correction protocol where we also have code switching into Z2 based codes. So this is obviously useful to code switch into Z2 codes because we can have the Clifford operators. So if we start with a Z2 code, we will basically take the physical qubits for Z2, Z2 to be the last 2 qubits on each edge, okay? So remember that we have this qubit mapping and we will take one of them to correspond to S and the other one to correspond to R, okay? Then we need to couple it to another n-2 qubits and initialize them to 0. And then we need to measure the stabilizers, okay? And this operation of doing these rounds of measurement will create this D4n code, basically by gauging a measurement. If we detect some errors, then they need to be corrected. And because of these non-abelian anion fusions, it's important to correct them time sensitively because a non-abelian anion can absorb some other anions. Okay, so we can't wait until the end of the protocol to perform the error correction. Then once we've corrected the non-abelian errors, then we're left just with abelian errors because of that structure of the commutators. Okay, so once we correct all the ones that violate these commutators, then we're left with commuting stabilizers, so with abelian errors, and those can be corrected normally. So in the D4n code, we can apply this logical gate on the logical qubit, and then we can switch back to the Z2, Z2 code by measuring the stabilizers for the n-2 qubits. Okay, so if we started with a plus state in this Z2, Z2 code, we can then obtain a magic state at this arbitrary level in the Clifford hierarchy. Okay, so we are actually working on some more details about the decoder, which basically generalized in this paper by Davidova, by Margarita and Dom and collaborators, where the threshold was also actually shown to be quite high by this numerical implementation by Julio, Noah, and collaborators. Now, for our codes, we actually will have n layers of anion fusions. So we need to do it, so we need to perform multiple rounds of this just-in-time decoder. And in particular, the time will scale linearly both with d, which is the code's distance, and also with n, like this number of physical qubits, which is the number, the level in the Clifford hierarchy. So in summary, we've seen that there are two approaches to construct arbitrary level gates in topological codes. One is hybrid lattice surgery, where we start with a stabilizer state for like a Z4N code, and then we merge and split it into a non-abelian code, and then teleport it into DZ2. And this enables teleportation of T to the 1 over n gates and magic states. Another procedure uses these automorphisms of group quantum doubles to perform constant depth gates. So whereas this one uses just nearest neighbor interactions, this one has constant depth gates. And the logical states are defined from these non-trivial configurations of anions, while the logical operation comes from a group 2 co-cycle with boundary counterterms. So we can get these constant depth topologically protected qubit gates, okay, which also admit a physical qubit implementation when the order of the group is a power of 2. So let's now come to some open questions. As we've already discussed, one nice question is related to the Bravy-Koenig bound, because the original Bravy-Koenig bound said that the level n of the logical level, like the logical gate, is equal to the number of space dimensions d when the level of the stabilizers is 1. So when we have Pauli stabilizer codes, we need to go to d space dimensions to get a level n equals d logical gate. We've shown in our codes that we can actually remain purely in 2 space dimensions, but increase the level of the stabilizers. So if we have level n-1 stabilizers, then we can get a logical gate at level n. So this naturally leads us to conjecture this generalized Bravy-Koenig bound, where the level n of the logical gate is equal to the level L of the stabilizers plus the dimension of space minus 1. Okay, we see that this reduces to the original Bravy-Koenig bound and to our codes. Okay, but can it be proven? And, or, can one do better? So is this the best we can do? If so, can someone prove it? Or can someone find some even better examples? Now, another question, as we've heard, is related to the just-in-time decoder, where, as I said, in our case, we have these multiple rounds of anion fusion, so we need to do multiple rounds of error correction. And then these non-abelian stabilizer groups, like how they are related to quantum error correction, because what happens obviously with a non-abelian group is that if we measure a stabilizer and then we measure another stabilizer that doesn't commute with it, it can change the eigenstate, okay? So it makes the error correction a bit more subtle if we want to use the stabilizer group approach. Finally, here I discussed these T to the 1 over n gates, but we can also construct constant depth control gates, like C to the 1 over n. And then, since this is a QID2026 conference, sorry to disappoint you, I have been talking about topological codes, but this means it's quite exciting to think about generalizations to QID2026 codes. And we actually heard a nice talk by Guan Yu, and we're thinking about some generalizations of this. Okay, yeah, thank you very much.
Okay, thanks for the nice talk. Questions?
So when you say beyond, you're considering high rate situation, or?
Yeah, sorry. Yeah, I mean, beyond, okay, this is one example, but, I'm sure that, I'm not sure, but I think there can be other instances of non-abelian QID2026 codes. And, okay, so the ones we heard from by Guan Yu were actually based on the Z2 cubed omega, so this abelian twisted quantum double. And there have also been other works by Nat and collaborators on using cup product approaches in these QID2026 codes. But what I've been talking about today has not been based on abelian groups of co-cycles and cup products. It was using non-abelian groups. So it's a bit different. And this is something we're just wondering, if they're like a QIDPC version of these codes, like what's the landscape of non-abelian QIDPC codes?
Sorry.
Can they be
what do you
defined?
mean?
Like we
Good-
don't even
good
know.
QL well, QL, I mean, code is already LDPC, so do you mean good QLDPC?
Yeah, sorry, good QIDPC codes. Yes, sorry, no, yeah, exactly. These are already low density parity checks, but the question is, can we improve their parameters?
Sure.
Can we get better encoding rates than just like 1 qubit? Especially since we have 1 logical qubit, but we need lots of physical qubits to get the higher gates.
Hi, I guess I'm curious if it's really fair to say D equals 2 for you. Because, I mean, yeah, you have a planar architecture when you have qubits, but the D in the qubit is varying, right? So when you express these as qubits, right? So I guess I'm unsure. There's a generalized Brobby-Koenig, I suppose, but does that apply uniformly for qubits in a fixed dimension?
Yeah, sorry. So here, I'm not okay. When we do this mapping, we still remain in 2 spatial dimensions. Like we're just putting more qubits on each edge of the lattice. We're not going in higher spatial dimensions. We remain on a 2D
like layering
lattice.
the lattice multiple times,
We don't
right?
have to layer it. Like, okay. I mean, one could think of it as layering, but you can also think of putting them like next to each other, like as arrays rather than as layers.
Yeah,
right?
but does it maintain planar geometry, the interaction graph? That's not clear to me.
That the interaction graph maintains linear geometry. So, okay, like these are the stabilizer operators. They're like these CZ. See, I mean, okay, for the X, it's CX, and this actually is just like binary addition, where you need to, first you flip the last qubit, then if it was 1, you need to flip the other qubit and like controls it. So, I mean, the stabilizers will have these type of qubit operators. Actually, we discussed some like 1+1D versions of these non-abelian codes with some Rydberg atom experimentalists, where they would just say, you can put them on an array on lines and then like implement these interactions between the codes.
Okay.
I mean, between the qubits. Yeah, but when we're not going in higher space dimensions.
No, I understand that.
Yeah,
but
but
like
I understand.
it is a QDIT where D varies in order to get deeper into the Clifford hierarchy. And I'm just curious, like maybe the conjectured generalization of Brobby-Koenig isn't quite right because of that. It's just a guess. I have no idea.
Exactly.
Yeah, it's very interesting.
It's a conjecture.
Yeah.
But the point is that if you like here, it's for fixed. Like if you want to obtain a gate at level n, then you fix your Hilbert. Like you don't need to constantly increase. Like once you fix the level of the logical gate, then you will have your like n physical qubits and level n-1 stabilizer
per site.
Per site and per site. Yes. Okay. Yeah. So for example, we haven't looked at like higher dimensional versions of these codes, but the reason is that we can get everything. Like we can get arbitrary level in 2D, but indeed it might be interesting, like especially from the fault tolerance perspective, as Rohe was suggesting, the single shot error correct, like code switching and error correction properties in 3D. It might be potentially interesting to look at like higher dimensional generalizations of this.
Yeah, maybe a follow-up on the previous question. So when I go to higher levels of the hierarchy, the code that I construct, just in terms of things like check weight, number of qubits, if you do a qubit embedding, is it correct to understand that the check weight remains the same? The qubit, like the number of qubits that you would need is increased by this factor of the local dimension n? Is that the correct interpretation?
Yeah, exactly. So this is the number of physical qubits on each edge is the same as the level of the logical gate. Okay, so if you want to go to one higher level, you need to add a qubit per site. But actually, the check weight also. But the check weight is constant in the QDIT description, but it increases in the qubit description.
I see. Okay.
Yeah. So they basically everything like scales by 1.
I see. And so in the qubit description, one would probably then expect like a reduction in threshold because of higher check weights, like the kind of the typical expectation in higher dimensions.
Yeah, exactly. So basically, like in terms of the error correction properties, for example, for the time, we expect it to scale linearly with the codistance as we expect, but also linearly with this number of physical qubits per site n. Yeah. And similarly, like the threshold, yeah, will go down with n.
Okay, so we have plenty of time.
Yeah, there's a question.
Oh, sorry. Thanks. Yeah, could you go back to the slide you were just on about the n thing? What's the switching when you're switching to D4n?
yes.
You always start from the Z2 times Z2 layer, and you just kind of gauge a different thing or have a different domain wall. Or
Yeah.
what is that domain wall between the?
Yeah, exactly. Okay, so the domain walls can be labeled by basically by two subgroups. So if we view it as a domain wall between D4n and DC2Z2, it's labeled by a subgroup which is D4n, and then the second subgroup is like Z2n generated by R squared. Okay, so basically when we go from here to here, like in the TQFT description, we like trivialize R squared. We take the quotient by the subgroup generated by R squared. So in the terminology where these are labeled by subgroups, it's like D4n and then quotient the R squared, and that leaves us with the Z2, where basically this is the image of R and then the image of S. Indeed, instead, when we go from Z2 to this, we need to basically do like a group extension of this Z2 by the normal subgroup R squared in D4n.
Mm-hmm. And
Yeah,
maybe,
so,
yeah, sorry, go ahead.
No, I mean, like we haven't written, okay, we're actually thinking about like the detailed like gauging implementation of this on the lattice. Here, I can tell you the kind of the mathematical description where it's basically the group and then you have the quotient by a normal subgroup generated by R squared. Like, so we know like the map of all the anyons and kind of things, but you know, the detailed lattice, so we expect a similar detailed like lattice implementation to the D4 case, but we haven't, you know, written this detailed lattice implementation of the gauges.
Mm-hmm. Maybe kind of related to this, the error correction, you were talking about doing many rounds with each one being kind of a Z2 extension. So you would match and then like do a concatenated matching, kind of like in the D4 one. But since you could kind of do this as an extension of some, you just do an abelian extension of some abelian anyons and just do one extension, right? Couldn't you just do like two rounds of correction, but one would not be matching, it would be clustering abelian anyons?
Yeah, I agree. Like you could start with a Z4n code and then gauge the Z2, right? Like you can get D4n by starting with Z4n and then gauging the Z2 charge conjugation. So I agree in that case, it would, you would start with all abelian anyons for the Z4n and then gauge the Z2 charge conjugation. That's similar to how one constructs like S3 or D4. Okay? But here we wanted to always like switch from N2 Z2 codes.
But I guess the switching is one thing, but then if you're just in D4n and say, just forget we even have switching just to do the error correction, I could use that structure of the like abelian extension of the abelian group to do just a 2-round error correction at the price of it not being like matching. I don't think it's an abelian extension. It's like an extension of some big cyclic group by Z2.
Yeah.
The result is an abelian, but you.
Sorry, it's not a central.
Yeah.
But
you
I mean,
can
it is
still
like
match.
D4n is, I mean, yeah, it is an extension of Z4n.
Well, yeah, maybe the question is the anyons of these double of D4n, they're sort of nilpotency class 2, aren't they?
No, the nilpotency class is n.
Oh, okay.
So
it's little n.
Yeah, it's little n. It's little n if it's a power of 2.
Big N is not a power of
Yeah, then exactly. It's not nilpotent.
Yeah, but I'm interested in the case where it's a power of 2, I guess.
Yeah, but the nilpotency class is n.
Yeah,
so
okay.
in particular, like the R conjugacy class anyon would then give you like the R squared conjugacy class anyon, which you then need to fuse again with R squared to get R to the 4, until you get R to the 2n. So that's why, like from the fusion rules, like R times R doesn't give you abelian anyons, because this R squared, if you're not in D4, is also a non-abelian anyon. I mean, if you're in D4, then R squared is abelian. Okay, so you just said nilpotency class 2. Oh yeah, sorry, this should actually be n-1 layers. So like if n is 3, which is the D4 case, you have 2 layers.
Okay,
If
I'm a little
yeah,
confused by that
sorry.
and the structure of you can get there in by just gauging abelian anyons once.
No,
I'll ask
no,
you
but
offline.
okay, you need to do multiple rounds. Like you need to do n-2 rounds. It's not that like here we drew it as once, but actually you need to do the round. Like you need to do a round for each qubit. Okay, so actually, you know, a more detailed way of drawing it would be, you know, to do it sequentially. Like here, like for each qubit, you need to perform these rounds of syndrome measurements for each extra-physical qubit. So the way I wrote it here is actually this kind of sequential operation.
But if you did the other switching you mentioned, which is like starting from a big abelian group and then doing one gauging, which is not the one you drew, but you could do that. I'm just a bit confused because that seems like it should say the anyons are like nilpotency class 2. But I can ask you offline.
Yeah, okay. Yeah. Thanks for the question.
Thanks.
Okay, any other questions? Okay, if not, let's thank our speaker. And this is the last talk of this session and today's talk. So let's thank the auto speakers today.